Okay, so what we're going to do is we're going to do an example of Gibbs free energy. This is our example. We're going to take magnesium carbonate, magnesium oxide and carbon dioxide. Delta H for this reaction is plus 100.6 kilojoules per mole, and delta S for the system we calculated earlier was 174.8 joules per mole per Kelvin. All we have to do is calculate delta G. So calculate delta G at 298 Kelvin. So this is how we go about it. Easy peasy. Delta H is 100.6 minus T. T, of course, is temperature. So 298 times delta S. Whoa, steady on there. This is in joules per mole per Kelvin. It needs to be in kilojoules. So what do I do to this number?
Divided by 1,000.
Fabulous. Divided by 1,000, which is 0.1748. So if we do that, we get 100.6 minus 52.09. Now I would strongly recommend keeping this, do this bit minus, keep this bit in brackets, because when this is a minus figure, it will, this whole expression will become a positive, so just watch that. We'll do an example of that in a minute, so don't panic. So if I do that, that gives me 48.51 kilojoules per mole. So, is this reaction feasible at 298 Kelvin?
Yes, it's positive.
That's absolute zero, isn't it?
No, 298 Kelvin
Oh,
is
no,
25
sorry.
It must have a negative value.
It must, yeah.
And it's not.
It's not
So
negative.
it's not right.
It's not feasible. It is not feasible
It's not feasible. It has to be the lower.
at 200
Don't you want us to
has to
put
be
a
a
plus
negative
in?
Don't we
value.
have to put plus, yeah?
For Gibbs, you can if you like. Yeah, really it's entropy that's really important, but you can put it for Gibbs. Right, so this is the next example. So we are going to work out, is this reaction feasible at 298 Kelvin? I've been told delta H is minus 890.3 kilojoules per mole. I need to work out Gibbs free energy at 298 Kelvin. I therefore need to calculate delta S. So first of all, let's calculate delta S. Delta S, remember, is the entropy of the products minus the entropy of the reactants. So, remember, it's the sum of the entropy of the products minus the sum of the entropy of the reactants. So let's do that. The products, I've got the table here. I've got 2 waters, so I'm going to put it in brackets 2 times 69.9 plus my carbon dioxide, which is 230.6, minus my reactants. I've got a methane, which is 186.2, plus 2 oxygens, which is 2 times 205.0. So, if we do that, hopefully we get minus 242.8 joules per mole per Kelvin. So I've got delta S, so I'm going to move on and now calculate delta G at 298 Kelvin. Delta H, they told me, is minus 890.3 minus T, 298, times delta S, but remembering I need to times this point by, so I divide it by 1,000, so that's times minus 0.2428. That's why it's useful to do that in brackets. So that's a minus times with a minus. So if I do that, it becomes minus 890.3 plus 72.4. And if I do that, it becomes minus 817.9 kilojoules per mole. So, is this reaction feasible?
Yeah.
You bet that this reaction is feasible. So let's have a think about it. This is methane with oxygen. If I came into this room with some methane, a bottle of methane, which is just the stuff that comes out of your Bunsen burner taps, and popped it on, would you get a spontaneous reaction with oxygen?
No.
If I just let it go,
No.
if you open up the gas tap,
Oh no.
does it immediately burst into
No.
No. Brilliant, it's the activation energy, so that's what I'm saying. So although it's feasible, really, really highly feasible, and you'd expect it really to be feasible based on delta H, because that's a very, very exothermic reaction. The activation energy is so high, so it's actually, until I start it, remember this tells me it's feasible once started, but I need to get that activation energy to start it. So there are two types. This is telling me about there's thermodynamic stability, which tells me about entropy, whatever, and there's kinetic stability, which is how fast it's going to happen. So although it's feasible, it's extremely slow.
But wouldn't every reaction be feasible if you have a big enough temperature? Because that'll make...
Not necessarily, and we'll look at that in a minute. Can you bear with me? Yeah, we'll look at it. So this reaction is feasible, but is... Some reactions get less feasible as I increase the temperature, which we'll look at in a minute, but is very slow because it has a high activation energy. So remember, this tells me nothing about rate. All it's telling me is in theory it's possible, but it doesn't tell me how fast it is.
So how can we tell it's got a high activation?
Yeah.
That's when you have to look at your rates unit. So you have to, you don't know that, you can't tell by looking at that it's got a high activation energy, which is why it's important to actually do the experiment. But this is telling me in theory the universe would be happy for this to happen. However, it takes a lot of, so it's like me saying it's feasible for you to walk to Edinburgh. However, who knows how long that's going to take you. So it's feasible for it to happen, but it could take you an extremely long time to do it.
How long?